This video is the third in a series about the AQA A-level Chemistry topic of alcohols. In it we'll look both at combustion of alcohols and at the chemical oxidation of alcohols. You might not immediately think of combustion when you think of the oxidation of alcohols, but of course it is adding oxygen to the alcohol, so it does count as oxidation. Alcohols are good fuels due to the additional oxygen that they contain when compared to alkanes, so they tend to burn very cleanly and undergo complete combustion. In doing so, they produce carbon dioxide and water. They can also combust incompletely to produce varying quantities of carbon monoxide and carbon particulates. You absolutely could have a 1-mark exam question asking about potential products of oxidation that includes reference to carbon dioxide or carbon monoxide. Of course, what most of us are thinking about when we talk about oxidation of alcohols is chemical oxidation, where alcohol loses electrons and produces one of several different products depending on the type of alcohol and the degree of oxidation it undergoes. We can classify alcohols as primary, secondary or tertiary, based on how many other carbons are directly bonded to the carbon with the hydroxy group. So for example, this is a primary alcohol because the hydroxy group is on a terminal carbon which is bonded to one other carbon. Whereas this is a secondary alcohol because the hydroxy group is on that central carbon and that carbon has another one on its left and another one on its right. So it's directly bonded to two other carbons. And then if we've got a carbon that has a methyl group coming off it, we can have a tertiary alcohol like this one. So that carbon that has the hydroxy group has a carbon on its left, a carbon on its right, and a carbon above it. So that makes it tertiary. So there are 3 options for our alcohol. It can be primary or secondary or tertiary. And this is important because it's going to determine what the product of oxidation is. So if we take a primary alcohol and oxidize that, then we're going to make an aldehyde. And if that aldehyde is oxidized further, then we can produce a carboxylic acid. In contrast to that, if we take a secondary alcohol and oxidize it, we produce a ketone. And a tertiary alcohol can't be oxidized at all. The tertiary alcohol could only be oxidized if a carbon-carbon bond was broken, and this carbon-carbon bond is much harder to break than a carbon-hydrogen bond, so it just doesn't happen. Aldehydes, ketones and carboxylic acids all contain a carbonyl group, which is a carbon double bonded to an oxygen, but the difference is the position and also what else is present. So in an aldehyde we have a terminal carbonyl group and then the other bond that the carbon makes is to a hydrogen. Whereas in a carboxylic acid we still have that terminal carbonyl group, but then it's also bonded to a hydroxy group. And then in a ketone that carbonyl group is coming in the middle of a chain. So we have carbons on either side. We name aldehydes and ketones in similar ways to the other organic compounds that you're already familiar with. So assuming no other functional groups, aldehydes are named using the suffix -anal. So this with 2 carbon atoms in its longest chain is going to be ethanal, and then propanal and butanal. You might be wondering, why is it not called butan-1-al? And the reason for that is that an aldehyde group has to be on a terminal carbon, so there's only ever one possible position for it, so therefore we don't need a number. If we take a ketone that has no other functional groups, then the suffix we're going to use is -anone, and this is going to be propanone, although you might have also heard it referred to as acetone, as in the stuff that's in nail varnish remover, and then this is going to be butanone. Now both of those don't have a number in them because the only possible option is for that functional group to be on the second carbon. With butanone we could count it from the right or from the left, but it would still be carbon number 2, so we don't need to include a number. But then when we get to pentan-2-one, now we do have a number because it would be possible to also have pentan-3-one. Chemical oxidation is brought about by using an oxidizing agent. This is shown in a chemical equation by an O in square brackets. So it isn't an oxygen atom, it's something that is itself reduced and is acting as an electron acceptor. Really common examples include acidified potassium dichromate and acidified potassium permanganate, officially called potassium manganate 7. You might also have encountered the use of hot copper oxide and then the 2 reagents that we use to test for alcohol type. So this would be Fehling's reagent and Tollen's reagent, which will oxidize primary alcohols to aldehydes and then carboxylic acids, but don't have a visible impact on secondary alcohols. If we represented these reactions with equations, then it would look a bit like this. So we'd start off with ethanol, and then we would have the oxidizing agent, and that would lead to the production of ethanal and also water. And then that ethanal could be put together with some more oxidizing agent, and then we would get ethanoic acid. Now sometimes we want ethanoic acid, and sometimes we want to stop the reaction when we've got ethanal. And the key to this is the reaction conditions. So if we're trying to get some ethanal, what we need to do is to have alcohol in excess and not use reflux. So if our aim is to collect the ethanal, or whatever the other aldehyde is that we're producing, we're going to need to distill it off as we're going through that reaction process. So the first thing is that we're going to have an excess of alcohol rather than an excess of oxidizing agent. And that's going to be in our flask, whether that's a pear flask or a round bottom flask. So excess of alcohol, a small amount of oxidizing agent, and also anti-bumping granules. And they're in there to make sure that we're creating smaller bubbles, stopping there from being large bubbles, which would make the reaction mixture jump into the condenser, which wouldn't be ideal. We've got a bung sealing the top of the flask, and the bulb of the thermometer is at that T-junction. So it's actually measuring the temperature of the gases as they go past. And we're aiming to only collect the distillate that has the approximate boiling point of the aldehyde that we are trying to collect, nothing higher than that. So the gases are going to rise up to that T where the thermometer is, and then they're going to flow down through the Liebig condenser. And you can see here that the water is going in from the bottom of the Liebig condenser and out from the top. And that's important because it's going to make sure that, that the water is totally filling up the condenser, and therefore that the condenser is cool enough. Because if we don't do that, then the product might not condense, it might just come out as a gas, and we might lose it all. It's also really important when you're drawing this that we're making sure that we don't have gaps between the flask and the bung and the condenser, and that everything is sort of continuous. And so we can have at the end, we could either have a collection flask, or here we've just got a beaker, and because we've got a beaker there, we've put it in an ice bath to cool things down even further, because we want the product to be as cold as possible to maximise the chance that we can collect as much liquid as possible and we're not losing it as gas to the atmosphere. Now, if we actually want the ethanoic acid, if we want the carboxylic acid, what we're going to need to do is to have the oxidizing agent in excess and heat this under reflux. So this is our setup for reflux, which is what we're doing when we're heating an organic reaction for a really, really long time. So you can see that it's open at the top because we don't want pressure building up, because that could be dangerous. And hopefully the condenser is going to stop us from losing too much of our product, but it will be better to lose product than have an explosion. So you can see we're open at the top there, and also just be careful when you draw this. You definitely haven't drawn a line at the top because that would imply that it's sealed. You definitely haven't drawn a line at the bottom, sort of showing the flask being cut off from everything else. You definitely haven't drawn lines closing off the two pipes of the condenser. So again, we've got water going in at the bottom and out at the top, and that's going to make sure that the condenser is totally full and that therefore things are being cooled as much as they possibly can. And again, we're going to have anti-bumping granules in that flask at the bottom where it's being heated, and that's going to make sure that instead of getting large bubbles that could cause everything to sort of jump up in the flask and jump up into the condenser, that instead we've just got very small bubbles. And we're also probably going to make a note that in this instance, it's our oxidizing agent that is in excess, not the alcohol. So my overall simple equation is going to be that we have our primary alcohol plus 2 of the oxidizing agent reacting to form the carboxylic acid, and that water that was produced in the first step where we made the aldehyde. So with secondary alcohols, we've got quite a similar process. We've got our secondary alcohol and then also the oxidizing agent, and we're reacting to form the ketone and also some water. There are two different tests that we can do to differentiate between an aldehyde and a ketone. The first test is the Fehling's test. So we're going to warm our chemical with some Fehling's reagent, and you make that Fehling's reagent by mixing together some copper sulfate, which contains that blue copper 2+ ion, and some potassium sodium tartrate and some sodium hydroxide, which is this colourless solution. You mix those together, warm your chemical with those, and if the chemical that you're assessing is an aldehyde, it will be further oxidised to produce a carboxylic acid, whereas a ketone can't be further oxidised. And in the process of that aldehyde being oxidised, the copper 2 plus ions in the Fehling solution will be reduced, and they're reduced from copper 2 plus, which is blue, to copper 1 plus, and they form a red precipitate. So if you've got an aldehyde, then you get a red precipitate, and if you've got a ketone, there's no change and you still have a blue solution. And then the alternative is that you use Tollen's reagent. So you make this by adding a small amount of sodium hydroxide to some silver nitrate, so you get a silver oxide precipitate, and then you redissolve that in ammonium hydroxide to make your Tollen's reagent. And again, you warm your aldehyde or ketone that you're trying to analyse with that Tollen's reagent, and the aldehyde can be oxidised to produce a carboxylic acid, and in doing so it reduces the silver, so the silver ions gain some electrons, and instead of being silver ions, which are soluble, they become silver atoms, which are insoluble, and that forms this silver mirror. So that's a positive test for an aldehyde, and again, for the ketone, we don't have a positive test, it just stays the same as it was before. Thank you very much for watching, and I hope you're now feeling very confident about your alcohols topic for AQA A-level Chemistry. If you did find the video useful, then don't forget to like, subscribe, comment and share for more A-level Chemistry videos coming soon.